Hello everyone, and welcome to our Newton's third law of motion post-activity. So, in the lab that we've been working on, we did some things with forces. And let's remember that we define forces as interactions between two objects, right, that result in some sort of push or pull. Right? And those forces result when that interaction takes place, whether that's by direct contact, right, literally a push or a pull, or some sort of more long-range thing like magnets or the force of gravity, right, where there's a field and the field exerts a force on the object. And those forces always come in pairs. There's force that one object puts on the other, and there's a force that's put back. Now, those have different names, and I'll talk to you a little bit here about what some of those names are, but I like to call them Newton's third law force pairs. Right? A concept builder guy calls them something a little bit different. Traditionally, we have a different name for them, but I like Newton's third law force pairs. Okay? See that? I stole that. Forces come in pairs. Physics. So let's take a look at a couple of examples and talk through the Newton's third law interaction that's taking place. Here we have a simple case of a book resting on a table. Now, of course, there's a Newton's third law pair going on here, right? These forces that result from interactions between the book and the table, right, results in simultaneously occurring pair of forces. So we know that the table supports the book. So we could say that the table pushes up on the book. We've called that a normal force. But the book is also doing something, right? If the table pushes up on the book, what's the book doing? Yeah, it's pushing down on the table. With this force, it's another normal force, I suppose, if you want to call it that. And there is a relationship between the size and the direction of those two forces, which is what we were looking at in the lab, and we'll generalize here in a moment. You with me? So the table pushes up on the book pushes down on the table. That's a Newton's third law pair. One interaction going on there. Are there other things happening? Sure. Right? But I'm focusing on one interaction at a time here. Let's look at something a little more complex. Say I'm swinging a bucket of water in a circle. Right? Bucket's attached to a string. Well, the Newton's third law force pair here would be that the string is going to pull in on the bucket, right? It's going to pull this way on the bucket. So by Newton's third law, what's the bucket doing? Well, it's going to pull out on the string. One force is on the bucket, one force is on the string. There is a relationship between those two forces. And so this is the pair. The string pulls in on the bucket pulls out on the string. See some patterns there? Now, force is a vector quantity, which means it has both a magnitude, a size, if you will, and acts in a particular direction. Newton's third law talks about the magnitude and direction of those two forces in every Newton's third law pair, shorthand here, right, in every interaction. Well, magnitude-wise, you saw a lot of examples in the lab, right? And all of those examples, what was true about the size of the forces? Yeah, they were always equal. Right? They were always equal. The table pushes up on the book just as much as the book pushes down on the table. Right? And you saw lots of examples of that. Direction? Well, table pushes up on the book pushes down on the table, right? Those are opposite directions. So what we've seen here is that these forces of interaction always occur in pairs which are equal in size and opposite in direction to one another. This is Newton's third law of motion. I know we skipped the second. We'll come back to that in a couple of units, right? Now we've done the first and the third. So here's my way of writing Newton's third law. In any interaction between two objects, the forces exerted are always equal in magnitude, which means size, and opposite in direction. A couple things about that statement. Note that it starts out by saying, in one interaction, right, between two things. And it says that the forces are always equal and opposite. And it says in any interaction, always equal in magnitude and opposite in direction. There are no exceptions here. And again, you saw that in the lab. It didn't matter how fast the objects were. It didn't matter whether they were pushing or pulling on one another. It didn't matter whether the masses were the same, which probably was one of the bigger misconceptions going in. Right? That's the one that usually threw people, was when you made them different masses and yet the forces were still the same size. Right? But you saw that in the lab. Now, this is not the pithy way that Newton wrote this. Of course, he wrote it in Latin in the first place. But the direct translation from the Latin, you may have heard this before. For every action, there is an equal and opposite reaction. So notice this has got the equal and opposite part in here. I personally don't like this more pithy statement because of the terms action and reaction. I don't like those words. You won't hear me use them, but you may see them, okay, from time to time. You take more physics, you may hear them. You're doing a concept builder, you may even hear them. Okay, but I don't like those because I think that makes people think like one only happens because of the other. Like one happens and then the other happens. It's not the way it works. Right? They happen simultaneously. Right? There's not one and then the other, there's both. It's the interaction that's happening here. And it also makes people think that the effects of those forces are what we're talking about, which it isn't. We're just talking about the forces. We'll talk more about the effects when we revisit Newton's third in a couple of units, once we get Newton's second. Okay, so I like this definition. In any interaction, the forces are always equal in size or magnitude and opposite in direction. Equal and opposite, Newton's third law of force pairs. Okay, now, this law seems pretty simple. Although, remember, before you did the lab, you probably would have answered or checked off those boxes a little bit differently, right? If I had just said, what do you think is going to happen? So, yeah, the lab's pretty convincing, but it's still a little counterintuitive, right? And there are some other things that we have to consider with Newton's third law, some complications here, right? Even though this law is simple mathematically, forces are equal in size, opposite in direction, things do get a little complex when we start to apply them. There is a classic story that was used for Newton's third law. It's called The Horse and the Wagon, a Newton's third law story. So let me tell you a little physics story. So it starts out in the morning, and a farmer wants to go and take his goods to market. So he hooks up his very smart horse to the wagon, hops up and says, "All right, horse, giddy up, let's go to market." But this is a smart horse and a somewhat lazy horse who does not want to pull the cart and go right to the market. So the horse turns around and says, "Suspend disbelief, please." Newton's third law says if I pull on the wagon exerts an equal and opposite force on me. Well, that's true, right? We saw that in the Tug of War. Right? You pull with a certain force, it pulls back with the same and opposite force, right? Equal and opposite force. Well, if those two forces are equal and opposite, when you add them up, they'll cancel. The net force will be zero. And if the net force is zero, and I'm starting from rest, I won't go anywhere. So I might as well not even bother. Now, obviously, there's something wrong here. You know that a horse can pull a wagon and go to market. Right? This is a possible thing, especially when it's on wheels, right? And that kind of thing. So you know this can happen. But the argument's pretty good, right? We know that whatever force the horse pulls on the wagon will pull back on the horse with a force which is equal and opposite. We saw that with the Tug of Wars. Well, things that are equal and opposite do add up to zero. So there's a problem here. What's the problem? Well, let's take these objects here one at a time and talk about this Newton's third law pair of forces. Right? What's the horse going to do to the wagon? Well, the horse is going to pull forward on the wagon. So this is the force of the horse pulling forward on the wagon. According to Newton's third law, though, if the horse pulls forward on the wagon, What's the wagon do? What's the Newton's third law pair to that? Yeah, the wagon pulls backwards on the horse. Okay, now those forces are equal in size and opposite in direction. Saw that in the Tug of War. But why don't they cancel? Why don't they cancel? Look at the diagram. Think about the other ones we looked at. Think about you right now, right, where you're pushing down on the chair, and the chair that you're sitting on is pushing up on you. Well, let's look at this situation. Of these two forces, how many of them act on the wagon? Just one. How many of them act on the horse? Just one. See what I'm saying here? These forces don't act on the same object. One of them acts on one object, one of them acts on the other object. And if the two forces don't act on the same object, how could they cancel? Right? If two forces are going to cancel, they got to act on the same thing. So the farmer can say to the horse, hey, look, Newton's third law pairs never cancel because they never act on different objects. In fact, if you're looking at two forces that are acting on the same object, they might be equal and opposite in size, but they're not a Newton's third law pair because they act on the same object. Newton's third law pairs are always the seat is pushing up on you, you're pushing down on the seat. The horse is pulling the wagon forward, you're pulling backwards on the horse. One force on the wagon, one force on the horse. Now the horse says, okay, you got me there, but you just said that if I pull forward on the wagon's going to pull backwards on me. And if I've got this force acting backwards on me, how am I going to move forward to market? Might as well just sit here. Well, that's why this isn't so easy. Nothing happens here in isolation. Some of you might have been thinking this was where I was going to go before, right? Except for the forces acting on different objects thing. Isn't there more going on for a horse to go to market than just the horse pulling on the wagon and the wagon pulling on the horse? Sure, there's a whole bunch of things going on. Right? For example, the earth is pulling down on the horse with a force of gravity. By Newton's third law, if the earth is pulling down on the horse, what's the horse doing? It's pulling up on the earth with an equal and opposite force. This is another Newton's third law pair. Do you notice how one force acts on the horse, one acts on the earth, so they don't cancel? The more important ones here are what the horse's hooves are doing. If it's going to go forward, it has to do two things. First off, the earth is going to, or the ground is going to support the horse. It's going to push upward on the horse. That's a normal force. And so the horse is going to push down on the earth or the ground. Horse is going to push down on the ground. Ground is going to push up on the horse. That's our support normal force. But that's not enough to make the horse go forward, right? Think about when you walk. Do you just push straight down? Try that. Stand up, push straight down on the ground and see if you go forward or backwards. You don't. Maybe you jump straight up in the air, but that's about it, right? You have to push down and what direction to go forwards? You need to go down, push down and backwards. So the horse is going to push down and backwards, which is actually a force of friction. It's got to rub against the floor here, right? If the floor was perfectly smooth, if the horse is on ice, it can't push backwards, right? Its hoof's just going to slip. So there's got to be some friction between the hooves, which always act, notice friction acts parallel to the surfaces. Normal forces act perpendicular to the surfaces. And if the horse pushes backwards on the surface with a force of friction, what's the surface going to do? According to Newton's third, it'll push forward on the horse. So notice here, there's actually 4 Newton's third law interactions going on here. The horse is pulling forward on the cart is pulling backwards on the horse. The earth is pulling down on the horse is pulling up on the earth with a force of gravity. The hooves, or the horse through its hooves, is pushing down on the ground, normal force, and the ground is pushing up on the horse, normal force. The horse is pushing backward on the surface of the earth, force of friction, and the surface of the earth is pushing forward on the horse. Another force, friction. So if we just focus on the horse, which is what we've traditionally done, right? Traditionally, we haven't drawn all these other halves of the pairs, but they're there. Right? Well, if we just look at the horse for a second, for the horse to go forward, what has to be true about the horizontal forces? Well, they have to be unbalanced, right? Because the horse isn't going to start to move. The velocity is not going to change unless the forces are unbalanced. And if the horse wants to go forward, right, this frictional force has got to be bigger than the force of the wagon pushing back on the horse. So how does he do that? So, all right, follow me here. The ground has to push forward harder on the horse than the cart pulls backwards, right? So that there's a net force forward, right? And the horse will move forward. Well, how does the horse do that? It's got to push backwards harder than it pulls forward on the cart. See what I'm saying? If the horse pushes backwards harder than it pulls on the cart, then the ground will push forwards harder than the cart will push backwards. And this will be bigger than that, like I drew in my diagram, and the horse can go forward. That's a lot, right, going on there. But it's something which the horse is able to do without really even thinking about it. But these are the forces, the interactions that are occurring in this process. With me there? Let's do another little example here that may be a little simpler. So this is me back in my Tug of War World Championship days. Not really, but, you know, that's me superimposed onto a guy. This actually is from the World Tug of War Championships. Yes, that actually exists. Right? That's why the guy is so huge. Right? So here he is, right? Classic Tug of War. He's got his ankles kind of dug into the ground here. You notice they're giving him support on his ankles so he doesn't break himself. Let's talk about what's happening here with the forces, right? Now, if this guy wants to win the Tug of War, he's got to move backwards. Right? He's got to move backwards. So that's his goal here. What do I do to move backwards? Well, most people in a tug of war focus on the rope. So what's the guy going to do to the rope? He's going to pull backwards on the rope. So this is the force of, in this case, me, pulling backwards on the rope. But by Newton's third law, if I pull backwards on the rope, what's the rope do? Yes, it'll pull forwards on me with a force which is equal in size and opposite in direction. Now, these forces don't cancel because one of them is on me and one of them is on the rope. Right? They're on different objects. However, right now, all that's acting on me is a forward force. If I was on roller skates, what would happen to me? I'd actually go forward. I'd pull myself forward along the rope, right? But that's not what happens, because that's not all I do. The guy doesn't just pull backwards on the rope so that the rope pulls forward on him. He also pushes into the ground. I'm just doing the angle. Technically, it's down and forward, down and to the left in the picture. But just to make life easy, he pushes forward on the ground, and so what's the ground do? Pushes backwards on me. So if we focus on me here, let's make this all about me, people. If we talk about me here, focus on me only. Right? I need this force to be bigger than that force so that I go backwards. How do I make this force bigger than that force? I have to be able to push harder on the ground than I pull on the rope. If I push harder on the ground than I pull on the rope, the ground will push backwards harder on me than the rope pulls me forward. I'll have a net force backwards, and I'll move, and I'll win. Now, of course, there's limits to how hard I can push on the ground without, breaking my ankles or sliding on the ground. There's limits to how hard I can pull on the rope, right, without, ripping my hands apart. But still, it's not just about the pull. It's also about the push. Back in the day when I was a younger teacher, back in the old high school, I used to physics at that point was like all seniors, almost all seniors. And so during like the assemblies when we do the tug of war, I was known to on occasion come down out of the stands, stand next to the seniors that were in the tug of war and yell at them to push, push, push. And the ones that were in my class would laugh, and the ones that weren't in my class would be like, what is this person doing saying push? I mean, usually in a tug of war, you go pull, 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 right? But I knew, and the ones that took my class knew, that it wasn't just about how hard we could pull. It's also about how hard we could push. One year, I watched the underclassmen come out for their first round. And I said to the teachers I was standing with up top, I said to them, hey, look, the underclassmen are going to win. They were like, what? Because they weren't the bigger people, right? They weren't the stronger team. But sure enough, they won their first round. And then the next round, they actually went up against the seniors, and they won that round too. Right? Why? What did I notice? Well, you ever been on a gym floor in gym shoes? Can get really slick. You can get some dust, right, on your shoes or on the floor. You ever notice how basketball players a lot of times are like licking their fingers and rubbing it on their shoes, right? And they're trying to make their shoes more tacky so that they stick to the floor a little bit more, so they have a little more grip. Well, what these underclassmen did was they came out, and as they came out, they all took their shoes and socks off. I don't know if you've ever been on a gym floor in your bare feet, but it can get rather sticky, right? Your bare feet on the floor. It's a little weird, right? You get stepped on or something like that, but I could tell that they were going to be able to make a bigger force with the floor than the seniors. So yeah, the seniors pulled harder on the rope, but all they ended up doing was sliding forward when they did that, because the underclassmen were able to push harder on the ground. Newton's third law. Yeah, in every interaction, the forces are equal and opposite, but sometimes you got to be aware that you have more than one object involved, and sometimes you have more than one interaction involved. And it's the net effect of all of the interactions that explains why an object moves the way it does. So I hope you enjoyed this little discussion on Newton's third law of motion.